Alright, so in our last chapter we talked about how the atom was structured in terms of what the electron cloud looks like. This chapter is going to be taking a look at how the electrons fill in that electronic map that we built together in chapter 2. And the reason that, and kind of how this came around to be, is that when you took a look at certain elements, so for example, if we kind of went all across the board and looked at a bunch of different elements, just some to name a few, you would see things like our elements here: hydrogen, helium, lithium, beryllium. I'm just kind of filling these in as we go. Not helium, that's neon. And then sodium, magnesium, aluminum, silicon, and then we would see things like phosphorus, sulfur, bromine, and argon. When we took a look at some of these elements, there was a gentleman that noted by the name of Dimitri Mendeleev. And one thing that Mendeleev came up with is he said, hey, there seems to be a trend. So for example, he said, I noticed that helium, neon, and argon all have similar properties. In addition, he noted that lithium, sodium have the same properties, as well as beryllium and magnesium, even as he continued to work through. So he noticed things like boron and aluminum had similar properties, things like fluorine and bromine had similar properties all the way through. And he saw that carbon was connected to silicon, nitrogen, to phosphorus, and oxygen to sulfur. And so what Mendeleev did is he said, all right, well, let's change the configuration. Instead of going left to right and just kind of order the different elements, let's take a look at this real quick. Let's say that I have hydrogen with its atomic number of 1, and I have helium with its atomic number of 2. Yeah, this one. And he said, well, I know that then neon and argon are kind of just like each other. I know that this should be chlorine, not bromine. It's my fault. He said, I also saw that fluorine and chlorine were similar, oxygen and sulfur, nitrogen, phosphorus, carbon, silicon, boron, aluminum, beryllium, magnesium, lithium, and sodium. And he said, this is actually kind of interesting because it followed the same suit. We saw that there were elements that ended up kind of having some general trends. And Dimitri Mendeleev is the first one to create a version of the periodic table that was grouped to say, or that was arranged so that each element was grouped by its chemical reactivity. And this was a really big deal at the time because they knew about all these different elements and they had these isolated chemical reactions, but they didn't really know much else about them. Everything was kind of like these one-off facts. And Mendeleev made a really big deal about this because the way he arranged his table by increasing atomic mass, And he even predicted the existence of undiscovered elements. And because when he filled in the rest of his periodic table with all of the elements that were known at the time, he left gaps. And so he said, well, I think there should be an element that behaves just like, say, germanium, but somewhere in between the other two elements of similar masses. And it turned out he was super correct. And this led to the development of kind of what the periodic table currently looks like. And so in this case, when we take a look at the periodic table, we're not going to go perfect with it, but it'll be close. And this comes all the way across here. There are these regions in the periodic table. And he said every time an element is in an element in the same column, will have the same chemical reactivity as the other elements in the column. And so what that means is when we take a look at things like lithium and sodium and potassium and rubidium, we'll say that all of these have the same chemical reactivity, or really similar reactivity. Same thing with things like fluorine, chlorine, bromine, and iodine. All of these elements in the same column have the same chemical reactivity. And so because of this novel breakthrough in how Mendeleev set up his periodic table and how we've adapted to it over the years, Mendeleev's periodic table laid the groundwork for the foundation of electron configuration. So in this case, Mendeleev laid the groundwork the foundation for discovering how electrons are arranged in the electron cloud. Or you might even hear this called sometimes electron configuration. And so this came around right after Niels Bohr figured out, like, hey, there are these quantum energy levels, and then quantum mechanics continued down this path of having sub-levels within our principal quantum levels, right? So if you'll remember, we'll see things like our atom is arranged with our principal energy level of n equals 1, n equals 2, 3, 4, 5, 6, right? And then inside this, we'll see that we have things like the 1s orbitals, things like the 2s orbitals, our 2p orbitals, 3s and 3p, and 3d, etc. Kind of working our way up. And so, based on this idea, and the way Mendeleev set up his periodic table, it was kind of set up that this allowed us to determine what the electron configuration of an atom would look like. And so to take a look at this, we're going to be analyzing some work by a few different scientists. So the first one we're going to be taking a look at is a concept called electron spin. And the Polyexclusion principle. So in this case, when we take a look at hydrogen, for example, we know hydrogen has 1 proton and 1 electron as a neutral atom. when we take a look at inside this, then that means we have our one electron probably in the 1s orbital. And we can think about this because of Coulomb's law, right? So Coulomb's law is effectively a fancy way of saying plus attracts minus. So we know things like the nucleus is a positive value, and so that way if we have a 1s orbital with our negative electron, we're going to probably have that electron as close to the nucleus as possible. And so when we represent this, we'll see that we can represent an arrow talking about the spin of the electron. In this case, when we take a look at an orbital, there's kind of a few fundamental important facts that we have to know. An orbital can only hold 2 electrons. And the electrons can only spin up or down. Up or down, and cannot spin the same way. And that's effectively what the Polyexclusion principle is. No 2 electrons can have the same quantum numbers. This right here is the Polyexclusion principle. It excludes electrons from having the same quantum numbers. So for example, if we're in the lowest configuration, I'm going to see that my hydrogen probably has an electron in the 1s orbital. And I can have this spin up, or I can have this spin down. Does it really matter which one? Not particularly. However, when I take a look at helium, I know that I have 2 protons and 2 electrons. And I know that my 1s orbital can hold 2 electrons, but they can't go in the same direction or have the same quantum numbers. So in this case, the quantum number that makes it different isn't the n, because n equals 1. We know L is equal to 0 because our orbital is spherical shaped. M sub L is 0, but now this M sub S, my magnetic spin quantum number, tells me it can either be plus 1/2 or minus 1/2. And so this plus 1/2 tells me I'll have a spin up, so like what we saw over here, or this will be a minus 1/2. And this is how I distinguish the quantum numbers from each separate electron. This is how I represent the distinction. And as I'll use that M sub S level. And so I would say that the quantum numbers for this electron pointing up would be positive 1/2, and the electron pointing down would have the N, L, and M sub L all the same, but the M sub S would be a minus 1/2. So when we take a look at this first concept, this Polyexclusion principle introduces the concept of magnetic spin of an electron and how the quantum numbers can't be different from each other. So now, though, once we get out of the first energy level, we're going to have to talk about a few other interesting phenomena that are occurring. So originally, when we took a look at our hydrogen diagram, we were able to get our orbitals set up to kind of describe what they would be if the other sizes. However, now we're going to start taking a look at what we call sub-level energy splitting. And in this case, and this is what we call a multi-electron atom. So not hydrogen, where it's way more complicated and we can't fully solve the Schrodinger equation. So one thing that's really important here is to say that in this case, we'll see that there are different values and different energy levels depending on whether we look at different orbitals. So in this case, if I'm looking in the same quantum level, I'll see that the energy of the s orbital is lower than the energy of the p orbital. And if they're there, we'll see that this is lower in energy than the energy of the d orbital and of the f orbital. So what that means is if I were to take a look at, say, the n equals 5 level, I would actually see that there's a different setup here. So if I were to take a look at the n equals 5 energy level, this would be my 5s, 5p, 5d, and 5f. And these all come about as a result of solutions to the Schrodinger equation. And so, based on these ideas, you can then start talking about, you can then start applying this to each separate level. We just use n equals 5 as an example because it had all of the different orbitals. But if I were to take a look, this whole piece right here is what that n equals 5 level has looked like. It's kind of divvied up into some smaller pieces. Now, one additional thing to remember is that we can actually use some further calculations. So in this case, we can talk about the attractions and repulsions quantitatively using Coulomb's law. So in this case, we said it's the fundamental form of plus attracts minus, but I can actually use Coulomb's law to predict the energy of an attraction between two particles. And it's a constant 1 over 4 pi e naught, epsilon naught, times Q1, Q2 over R. So in this case, the E is the energy of the attraction or repulsion. So how strong is the attraction between the plus and minus? In this case, epsilon naught is a constant. That constant is that it's 8.85 times 10 to the negative 12 coulombs per joule meters. Coulombs squared per joule meters. We'll also see that Q1 and Q2 are the charges of the ions attracting, or in this case, the charges of attraction or repulsion. And then R is the distance between the charges. And so what this just says is that when I have a plus and a minus far apart from each other, we're going to see that this is a really weak attraction, or we'll see it's a weaker attraction compared to if my plus and my minus charges are close to each other, and I'll see that this is going to be a stronger attraction. And so when you use this to solve everything out, we can kind of help map out our sublevel energy splitting a little bit more. So in this case, there's the attraction that holds these together. However, there's one repulsion idea, or another idea we have to talk about. So in this case, we can see that there's the attraction between our pluses and minus, but there's one more effect that occurs. We can see one more thing called shielding in the atom, versus we can look at penetration of the atom. So in this case, we're going to take a look at two examples. In this case, if I take a look at the shielding, we're going to take a look at lithium atom, for example. So lithium atom has my 3 protons, and I know in the first energy level, it's got 2 electrons and an electron on the outside in the second energy level. In this case, when we take a look at the pull that is experienced here, we have these 2 electrons we'll see that these two electrons, we can kind of use in this case, they feel the effect of a +3 charge. But when we take a look at this electron in the second energy level, we're going to see that it only feels the effect of a +1 charge. And that's because the two negatives in level 1 cancel out two of the positive charges. So what we kind of see is that there's kind of like a feeling effect of only having a +1 hold this electron in. So what does this mean then for kind of how our electrons are set up? Well, effectively what this says is that electrons are closer to the nucleus are held a lot tighter. So when we take a look then, we're able to kind of get a general mapping of what our atom looks like in terms of full orbital energies. So when we account for all of the shielding, all of the penetration, Coulombic attraction, we talk about the charges and effects of everything. When I take a look at the diagram of the atom, or an orbital diagram of a multi-electron atom, it's going to look a little different than it did for hydrogen. So I'm going to take a look. Here's my axis of energy, generally increasing. And I'm going to see that my 1s orbital is the lowest orbital that we have. Next one, I'm going to see that my 2s orbital and our 2p orbitals are next. After that, we'll see we have our 3s orbital, our 3p orbitals, and our 3d orbitals. And this is going to continue to increase. When I take a look at my idea now, I'll see that my 4s is a little bit higher than the 4p, but the Coulombic attraction says that the electrons in the 4s feel more than what they felt in the 3d. So we actually end up with my 4s electrons in between there, and then I have our 4p's that are a little bit higher in energy than 3d. And same thing, we'll see the 4D electron system. And this pattern kind of continues as we move up the atom, especially when I take a look at 5s. I'll see the 5s orbital is actually a little bit higher than the 4p, but definitely lower than the 4d. And we'll see that this system continues across the board. So a couple important things in vocab words. You'll notice that sometimes when we take a look at the 2p orbitals, like we have a 2p in the x direction, 2p in the y, 2p in the z, or along the z-axis of a three-dimensional graph, whenever I have orbitals that are the same energy, they're called degenerate orbitals. So I have my degenerate orbitals are all orbitals with the same energy. So all three of my 2p orbitals are degenerate. All 5 of the 4d orbitals would be considered degenerate. So in this case, when we consider all of the effects of shielding and penetration and Coulomb's attraction, this is the general map that we observe. So now, what we can do is we can use this orbital diagram to figure out what the electrons should look like in our electron configuration. So what this means then, there were kind of a couple other chemists that took this idea and ran with it as they started to develop the mapping of the multi-electron atom. And they said, okay, when we fill this in, there's a couple rules. Coulombic attraction, or Coulomb's law, says plus attracts minus, so in this case that means we fill from the bottom up. And this was originally developed by a guy named Hun, so they call this Hun's rule. I fill from the bottom up. And the other thing that comes with this is that I have to make sure all degenerate orbitals are filled once before they're paired. So when we take a look at this, if I were to take a look at, say, if I were to take a look at the element nitrogen, for example, nitrogen has 7 protons and 7 electrons to fill in. So I would follow Hun's rule and the Polyexclusion principle to fill in my electrons. And we're going to fill in our electrons in black. So in this case, in my 1s orbital, I have to put 1 up, 1 down, because there's no other degenerate orbitals. Same thing with the 2s. But now, when I get to the 2p, I have to fill in my electrons one at a time, because Coulomb's law says I fill from the bottom up. And the other half of that is that this negative electron repels the other negative electron. So I'm going to spread those out around the 2p's before I start to fill them up again. If I were to take a look at what the diagram for oxygen would look like then, it's going to be 1 further. If I were to take a look at oxygen, which has 8 protons, 8 electrons, I would follow that same pattern. My 1s orbital fills first, followed by the 2s orbital, and then the 2p orbital. So now I have 4 more electrons to fill in, so I go 1, 2, 3, 4. So in this case, I waited until all of my other orbitals were filled before I started pairing with an opposite quantum spin number. And the way that we can summarize this is then we can kind of write out a short version of our electron configuration. I can write this out as an electron configuration of 1s2, 2s2, 2p3, because I have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 3 electrons in the 2p orbital. And when we take a look at the electron configuration for oxygen, it would be 1s2, because I have 2 electrons in the 1s orbital, 2s2, because I have 2 electrons in the 2s orbital, and I have 2p4, because I have 4 electrons in the 2p orbital. And this is going to be, and this kind of led to a really big deal because it helped us start to figure out some periodic properties and how our electron configurations led to the periodic table and its current setup. And that's what we'll take a look at in our next video.